Okay, so hello everyone, myself Shovik Mundal, and I am currently a PhD research scholar in TIFR Mumbai in working in theoretical physics department. And I actually love to solve various problems not only in physics or maths also. So currently I am creating this channel for solving various interesting problems from different competitive exams like GATE, NET, JEST, JAM, etc. I have some decent achievements on this exam, so I actually decided to creating this channel to help you guys and also to help myself. Suggestions are always welcome. Your knowledge is also welcome for me, and that's why I am creating this channel. And currently, many of you go through the CSIR NET 2024 exam. So, in my first video, I will try to solve a problem from CSIR NET exam, and in the next videos also, I will try to solve more problems from CSIR NET exams, and some good problems, some difficult problems also. and uh, and I also try to create my WhatsApp channels and Telegram channels. You guys can join those channels. I will share the link on description, and you guys can join and discuss problems, solve problems with me and others also. So okay, now let's start the solution of the CSIR net one CSIR net problem. Okay, so the problem is from quantum mechanics, the delta function potential problem. Okay, so this is the problem. Okay, the problem is like the given wave function is root under alpha e to the power minus alpha mod x. This is definitely a delta function potential. Many of you are actually knows this. This is a negative delta function potential, and we have to calculate the ground state energy. Okay, so this is a standard problem of solving Schrodinger equation, and many books have this solution formally. So I am also discuss these solutions in step by step in a very detail. And in the next video, I will try to do another a good problem in this delta function potential, which also comes in this NET exam, NET 2024 December exam, and that is actually a very good problem. And we have to calculate some phase difference of t plus and t minus. That is the kind of problem, I actually can't remember it, but that is actually a very good problem on delta function potential. So this is the basic problem of delta function potential, and in the next video probably I will upload the solution of the another problem of delta function potential which comes in this net exam. Okay, so now solve this have to solve this. So this is the delta function potential, and its range from 0 to minus infinity. So the first thing I want to mention that if I want to uh, if I want to have the solution for bound states, the bound state definitely should have negative energies. So option 1 and option 4 are the only possibilities. Option 2 and option 3 will definitely not be correct, because your potential has range 0 to minus infinity. If your energy is negative, then only bound state can exist. Otherwise, there will be a scattering states. So E is positive, not acceptable. So we will work with E is equal to negative. So this 1 and 4 could be the right solution. So now do it formally. So this is our Schrodinger equation. The Schrodinger equation for x naught is equal to 0 is given by this. This is minus h cut square by 2m d2 phi dx2 is equal to minus e phi. And minus e is for the bound state, I already mentioned. Thus minus sign takes care of that it is a bound state. Okay, so this is a standard solution of the superposition of e to the power kx and e to the power minus kx of type, where k square is 2me by h cut square. And for x greater than 0, we already have done this many times actually. So at x tends to infinity, phi should vanish because we want a valid wave function. That's why the right psi r, which is the right hand side solution, is a to the power minus kx. And for x less than 0, that is x tends to minus infinity, psi also should go to 0. So the left hand side solution, that is psi l, is equal to b e to the power kx. Now the continuity of wave function at x is equal to 0 gives us a is equal to b. So this is the graph of the wave function. This is the decreasing for x greater than 0, and this is increasing for x less than 0. Many of you know this solution. Now the most important part comes here. The most important part is the momentum will not be conserved. at x is equal to 0. The momentum will be discontinuous at x is equal to 0, and this is the trick we have to use now. So this is the Schrodinger equation, usual Schrodinger equation, and now we have to integrate this equation from a very small neighborhood of 0. The neighborhood is minus epsilon to plus epsilon. So epsilon is a very small neighborhood around x is equal to 0. And in this limit, we actually have to integrate this whole equation. So the first term will give like this. Let me explain how I can get this solution in different page. And let us look at the second term. The second term is minus lambda delta x psi dx, and the range is minus epsilon to epsilon. We already know how to integrate this. And the last term is e into integration of phi dx minus epsilon to epsilon, where you can split this phi in phi r and phi l. Phi l is the left hand side solution and phi r is the right hand side solution. And you can set the limit accordingly, minus epsilon to 0 and 0 to epsilon. Now, if you take the epsilon tends to 0 limit, then this phi will surely vanish. You can check that. If we integrate, this integration is very easy. You can put epsilon, you can put 0 the limits properly, and if you take epsilon tends to 0, then this term will surely vanish. You can check that. And this term is the usual delta function integration. You know that how the solution looks like. And the integration of d2 phi dx2, this is actually d phi dx. Now, when you have d phi dx and the range is limit is minus epsilon to epsilon, so when you put x is equal to epsilon in the first term, phi goes to phi r, because phi r is the solution in the right hand side of x is equal to 0. So the first term is d phi r dx, and the second term is see only d phi l dx, because when you put x is equal to minus epsilon, then phi will be phi l, the left hand side solution. So this term will be d phi r dx minus d phi l dx. So now we have this solution, this whole equation. The right hand side already goes to 0. So the left hand side you have to take the differentiation of d phi r dx and d phi l dx, and put x is equal to 0, because the limit epsilon goes to 0. So this is the value of this is the differentiation, and you have to put x is equal to 0. This is the delta function integration, which you can already we have to put x is equal to 0, and the right hand side is 0. So this is very easy actually. You can now, this is a simple algebraic equation, and you can solve it. Then you can finally get that lambda is equal to h cut square k by m. So k is equal to m lambda by h cut square. So finally you find that k in terms of lambda. Now you know that the ground state energy is minus h cut square by 2m into k square. So in the place of k square, you have to put this m lambda by h cut square, and after putting it, you finally get that the ground state, that is minus e is equal to minus m lambda square by 2 h cut square. Okay, so the correct option will be option D.